Hi guys, welcome to the second lecture in a series of lectures about MASD and model-driven engineering, MD. So as I said in a previous lecture, if you missed it, the objective of this series of lectures is to try to give you the theoretical background required to understand what it is that we're doing in Dogen. So it's sort of a dual purpose really. It serves as a preparation for my Viva, so I'm revising a lot of things that I've bumped into in the past. It also acts as a way of allowing regular software engineers, people that are not particularly interested in these sort of technologies, to just have the basic requirements, the basic knowledge needed in order to contribute to Dogen. So it's kind of an outreach exercise. So in the previous video, we sort of introduced most of the basic concepts of model-driven engineering and explained the historical context. When I say we introduced, I mean we just mentioned them really. We talked about things like models, meta-models, meta-meta-models. We explained the abstraction road that we've been on in computer science from a long, long time, and where we are, and where model-driven engineering is trying to take us. We didn't really spoke too much about the concrete sort of implementation level aspects of it, which is not really part of this introduction. It will be part of the second, well, the third video, hopefully, third lecture. I'd like to a few things I wanted to do in the previous video I didn't do is because I had to go through my shelves and find things. So I'm quite interested in the history of computer science. I've always been, to be honest, but I think people like Evelyn, Henney, and some others in our sort of environments, they are quite useful because they serve as a bridge between the past and the future. They try to explain a lot of the concepts that happened in the past and how they relate to the stuff we're doing right now. So if you haven't, I highly recommend any of the talks from Kevlin. I'll probably link a couple, probably my favorite ones. But I do think you probably want to watch most of his talks because I think they're, as a bridge between the past and the future, they're great. But at any rate, other than watching his videos, the other thing I recommend is books as well, if you're interested in this sort of stuff. I'm going to just quickly go through a few books that I think it will give you the right context of the stuff that's happening, or the stuff we spoke about in the previous lecture. So one of my my absolute favorites is Tracy Kidder's Soul of a New Machine. This book is, well, I guess in historical terms it's probably recent because it's more like 70s, but it describes how software projects worked in the days of low-level hardware and software integration. I mean, I can't say enough about this book. It's just, as a novel, it reads really well, but as a book for computer nerds, it's quite amazing, I think. I think that programming is one of those things you fall in love with, and these books really help you because they show other people with the same sort of view of computer science and software engineering as you do. So that's definitely one I recommend. Equally, a little bit. Well, this book spans that era and goes a little bit further. Hackers is another classic. If you like Lisp and you like Emacs, I think you really should read this book. It explains all the stuff they were up to in the MIT lab. In fact, to be honest, I think if you were to try to sum up the core inventions and the core modern concepts of programming that we use these days, I think there are probably three labs. I've probably forgotten to put here the Bell Labs book. Sadly, it's not very easy to look for things here, so I'm not going to do it now. But there is a book about Bell Labs, which I also consider to be crucial. You know, of course, I'm going to have to try. Yes, okay, I did find it. So I think if you want to understand the three labs, this is good for the Bell Labs, the Idea Factory. It's very good to give you the context of what was going on in the Bell Labs. This is good for the MIT lab, hackers. Explains very well what's going on in the MIT lab. And then, of course, you couldn't really skip Xerox PARC, Dealers of the Lightning. I think this book is absolutely amazing. I can't really tell you which one is my favorite of these three books, of any of these books really. I highly recommend you read them because if you really want to get a context of where we are, you should try to read that. Then, in terms more of this, going further back in time slightly, then I recommend two other books. The Superman. When I was talking about people programming in binary, Seymour Cray actually once well, this is part legend, part true, I'm not sure. But according to legend, Seymour Cray once bootstrapped an operative system of a computer that he designed using only the switches in front of in the front of the computer. So in other words, in binary, he bootstrapped the entire operating system in binary from memory without making a single mistake. So it's not even hexadecimal; it's in binary. That's the kind of person Seymour Cray was. So I highly recommend reading up on that. And finally, The Dawn of Software Engineering. This book is good if you want to correct the historical record and if you want to really understand who did what when. Now, one big problem with all these books, which I think is a really, really big problem, is that these are all books about men, and mainly American men. It really skips almost all of the history that involved women, and if you don't know too much about the history of computer science, then you'd be surprised to know that women are core to the history of computer science. So much so that even the word computer was applied initially to women that were working in computer science. They were the first computers. Ada Lovelace was, of course, the first programmer. And I do have a book about Ada, but I'm not sure what that is right now. So I will do an effort to complete what's missing in my library. I will probably start buying some books on that side. There's quite a few very good books that are on my list that try to correct historical record. But the reason really why I started talking about these books is I want you to understand that when I talk about history here, I'm not really talking about that kind of history. The history in the precise sense of recording what happened when and who did what is not quite what we're looking after here. Instead I'm talking about more of the waves of thinking and the coarse-grained movements that happen in history. So when we move, for example, from say I don't know, plug boards to assembler to machine code, I'm not necessarily saying that's the historical record. I'm just saying that if you were to look at history from a broader lens, you'll see groups of ideas coming together, and that's what I meant in the first video. So just in case anyone is thinking that I'm talking about explicit days and times and the history actually occurred exactly like that, that's not quite what happened. But for the purposes of our series of talks, that is sufficient. That's a sufficient approximation that enables us to progress. So now that we've done that, we can go back to where we were, which I believe we were talking about technical spaces. So what we will do now in the next set of slides, or the rest of the talk today, we will try to talk about some of the fundamental concepts. I mean, we've already introduced meta models and meta models and so on at a very high level, and so we will now talk about a couple of other concepts that for model-driven engineering, well, to be honest, for MASD, they're quite crucial. Model-driven engineering is actually quite a broad field, and part of my thesis is a critique of the difficulty in trying to grasp MDE, because it's quite vast and it's difficult to know where the boundaries lie, as we shall see in this series of lectures. So I'll just introduce a few concepts just so that you can make sense of a lot of what we're saying. So we start with technical spaces. So as far as I could locate in my bibliography, Kurtev was one of the first people that started talking about technical spaces. And the idea of the technical space, I'm sure there would have been other people talking about it before, but the idea of a technical space is the notion that there's a grouping of technology that goes together. Normally, the best way to think of a technical space, at least in my mind, I normally tend to think of a technical space closely associated with languages. And languages here, I use the word quite broadly. So for example, if I think of C++, I think of C++ as a technical space. I think of Rust as a technical space. The reason why, in my mind, that's how I look at it, is that in C++ you have a math model of the language. We have also a set of libraries. And you also have sort of a way of doing things. So there's a bit of culture, there's a bit of physical things that come with the technical space, and there's also the meta model and the technical and specification aspects of it. And then the idea with technical spaces is that a project will probably span multiple technical spaces, but these technical spaces will be of different kinds. So for instance, you could have, I don't know, in RDBMS you could have SQL as one of your technical spaces. I mean, SQL really is not really a specifically technical space. It'll probably be something like PostgreSQL, I guess. You will also have something else as technical space, perhaps CMake, because you need to have some build files for your C++. And so your project, your product will be composed of a set of technical spaces. And each of these technical spaces can be segmented away. And the idea then being that once you think of the world in that sense, in terms of technical spaces, you can then start to think of bridges between technical spaces. So if we go forward a little bit, so if you think of it this way, then if you think of a meta model and a meta model, or more, one or more meta models, and if you think of all the things that come out of those meta models, in other words, once you start instantiating the meta models, you're going to create specific code for your system. All those things are bundled up together in that technical space. So you could have, I don't know, an application in Java, an application in C++. Those would be two different technical spaces. And then you'd have a whole associated paraphernalia of infrastructure in XML, which also be in a separate technical space. And as a programmer, most of the time you're in and out of technical spaces. Each technical space has got their own context, and that normally means their own vocabulary. So the more precision is required, the more you need to be inside of a technical space, because you need the context to give you that precision. Now, it may sound that the notion of a technical space is a very wishy-washy notion, and to be fair, a lot of the definitions that we're going to find in model-driven engineering are not definitions that are they're not very easy to grasp, because well, you may start to ask, why do I need this definition, and what exactly does it mean precisely, and so on. And you'll see that a very large percentage of my time was taken trying to understand exactly what is MDE and exactly where it starts and where it ends, and dealing with the fuzziness of these definitions. And we will talk about all of that in a subsequent lecture. But for now, all I want you to understand is that there is a need to distinguish between technical spaces, because the idea of the technical spaces is, what we're trying to do is we're trying to do a taxonomic characterization of the problem space. The problem space of MDE, as it turns out, is the problem space of software engineering. And it's very important for us to get the right language in order to be able to characterize the technical space, the problem domain, so that once we try to propose solutions, we have the vocabulary needed in order to understand the context of the solution. So part of this dichotomy that we have in model-driven engineering is a very strange one, because in one side we are trying to be super precise with the SLs and strict meta modeling and modeling and that sort of thing. But on the other hand, there's also a bit of a social science, in the sense that we need to do a lot of this not particularly precise classification and taxonomic work, and it's the junction of the two that end up making model-driven engineering. So if you equate more or less a programming language as a technical space, you're not going to be far wrong. It's slightly more abstract than that, but the idea is kind of at that level. And of course there is a zoo of technical spaces. I'm not going to go too much into MDE here, but right. So actually, one thing that we missed in this presentation, which I'm going to cover, although it's not in the presentation, I'm going to cover very quickly. The second concept that's related to technical spaces are platforms. Now we have a whole chapter on this, which we'll deal in more detail later. But I'm just very quickly going to cover. These images are quite helpful as well. So as I mentioned before, we have these technical spaces such as model-driven engineering, which is a very, very vast and amorphous technical space. And then the more concrete technical spaces are Java and XML and things like that. I don't even think it's probably correct to call MD a technical space really, but I think that's fine. Then we have the notion of platforms. And then, well, if we look at the technical definition of what a platform is, then a platform is a set of resources on which a system is realized. And this is basically a set of resources used to implement or support the system. Now, that sounds very vague, and it is actually quite a vague notion, but you can probably think of a platform in the sense of CLR, for example. You can think of the Java JVM as a platform. You can also think about, and platforms are built on top of platforms. So, for example, J2EE is built on top of JVM, and so on, right? So, the platforms stack each other, and the more important concept of the platform is the platform is trying to provide you with a raising of the abstraction level. So the technical space is basically is the place where all the technology gets bundled up together. The platform is the thing that raises the abstraction level, and in some cases the platform could span multiple technical spaces. For example, J2EE uses a lot of XML. But the most important thing about the platform, which is different from the technical space, is The platform raises the abstraction level. So in the past we spoke about this continual raising of the abstraction level that characterizes computer science and software engineering, going all the way from assembler to high-level programming languages. Well, once you get to a high-level programming language, the next level of raising of the abstractions is via the platforms. For instance, an operative system is a platform because it allows you to ignore the hardware, because the kernel is there to manage the low-level things for you. And then, of course, the JVM is built on top of the operative system, or it runs on top of the operative system. So in some ways, it allows you to ignore the operative system to an extent, and it's got things like libraries that enable you to interact with the kernel. So once again, your abstraction level has been raised. And then, of course, there's libraries that make use of other libraries and so on. So the base class library in C# is used by, I don't know, say, all sorts of libraries, Windows workflow, for example, to give you a workflow engine so that you can create workflows for your processes, and so on. As you can see, the platforms start stacking up on top of each other to give you a higher and higher level of abstraction. And their notion is that at some point you're just going to be able to talk in terms of your domain. The higher, the further up you are. Of course, there's a lot of things can be said about this. You could criticize this in many ways. Kevlin does a very good job of criticizing the notion that abstractions need to necessarily be stacked on top of each other. For example, we tend to think of the machine as a low level and the problem domain as a high level of abstraction, but he makes an argument that maybe you should think about it the other way around, that the machine is actually the high level of abstraction because you're really, really far removed from everything, and the domain is the low level of abstraction because actually that's very close to reality. I think that's a really good point. The other thing as well is that this notion of things being built on top of each other is a notion that we created, and it limits the way you think slightly. If you're a mathematician, you wouldn't say that maths is stacked on top of each other. You wouldn't say that set theory stands on top of something else, or calculus stands on top of something else. You could say that one technology within maths makes use of other technologies. You could maybe make an argument for certain things to be more basic than others, like say arithmetic. But the mathematician looks at a maths as a flat space. And if sometimes you need abstract algebra, you would make use of abstract algebra just like you make use of algebra. There is no need to create a hierarchy, although conceptually maybe you think of it as a hierarchy. Whereas in computer science, we spend a lot of time trying to convince ourselves that this hierarchy is quite rigid. I mean, if you remember when we were talking about the metamodal hierarchy, we said that there was sort of a layered approach to models, and we implied that a model, for instance, shouldn't really be using concepts of a meta-meta model. Just keep in mind that like everything else, was defined by somebody, and it's been accepted, but it's not necessarily the truth. It's just a convention that we all adhere to because up to now it's been useful in organizing our thinking. But it's not necessarily the only way to do things. And of course you could say the same thing for almost all abstractions. You can make a critique for the current systems. I mean, you probably noticed that even Linux, which is my operative system of choice, it's quite bloated these days. I mean, I used to run Linux the 99, 2000 in 16 gigs of RAM, 16 megs of RAM. And I was able to boot Linux. I was able to get into X Windows, X.org as it's called now, X3 in those days. I used to be able to get into the operative system, and I still had space to run things like compilers. It's hard to even imagine how that was possible. Now, these days, I'm not sure how much the kernel takes, but it's probably much more than 16 megs. GNOME is probably going to be hundreds of megabytes. Gigabytes is not unheard of. A browser would definitely take several gigs. So we paid the cost for these abstractions, and the cost that we paid for these abstractions was that complexity was one of the side effects of these abstractions. So it's not necessarily that all these things should be seen as a natural progression of thinking. It's just it happened this way, and it happened for a reason, because it allowed us to think quicker about things. But it's not necessarily the end of the story, I don't think. So resuming to what we were talking about today, then we've introduced technical spaces in platforms, and we are going to try to stick to an hour on this chapter, on this lecture. So what is interesting about MDE? I mean, we've only introduced MDE very quickly, very briefly, but what it is, I'm already going to start talking a little bit about the critique. I think it's important to start with the critique because you may be a bit uninterested in these lectures, this series of lectures, because the first question you'd say is, well, I've been programming for 20 years, and yeah, I've heard of UML, and maybe I've heard of, I don't know, MDA or something like that, but that's all the stuff that we used to do in 2000s and so on. No one really does any of that anymore, so clearly you're talking about something that's not particularly useful. And I would not blame you for thinking that. In fact, I wasn't even aware that MD existed when I started researching on code generation. It's so let's look a little bit as to why, where MD is really. So as you can see, it's a lot of these ideas are super clever, but if you work in a professional environment, you notice by now that you're not actually doing anything with model-driven engineering, at least not with that name, at any rate. We we've got the usual quotes from those in the field, such as Meller, which is a very funny character. Meller basically says that MD will be commonplace in 3 years' time, but we are saying that every year or every 3 years. So it seems like model-driven engineering and AI are similar in the sense that well, actually, of course, AI now is associated with ML. But for all the people like me, people that were around on the previous AI bubble, AI was supposed to solve all the problems in the world, and for a very long period of time, it was always around the corner, and it took many years. If you think that the Lisp guys, well, Lisp was literally created by McCarthy in order to implement some of his ideas around the AI, and that was in the 60s. And I think that would be fair to say that maybe in 2010, 2020, that's been the first time where AI became practical at a large scale. You can see it took a very long time for a lot of these ideas to become useful in practice from a software engineering perspective. So it is possible that MD is either like AI, and it will take 50 years until we can really truly understand, or it could be that it's like other ideas in computer science that just never took off. And so the question to ask really before you invest any of your time in it is why has it not yet taken over? So there's a few explanations for that. So some people say that the theoretical models are not complete. In other words, there is no theory of modeling like there is a theory of computer science of compilers. So if you think of compilers, compilers are always used as a proxy, and I use this a lot in my research work. Compilers are used as a proxy for the sort of work that we want to achieve with model-driven engineering. The notion being that with a compiler you create a formal way of translating high level to low level, and you could get very close to proving from a mathematical perspective that your compiler is correct. I'm not going to get too much into the mathematics of compilers because we don't really need that for these purposes, but if that's your field, I'm sure you're going to say that there's loads and loads of technical details there. Let's just ignore that for a second, but let's just think of compilers as the limit of the function that we're trying to get to, because from the perspective of MD, compilers are much further advanced than anything else that we are doing right now. And the idea is to try to get to some kind of theory, a bit like a compiler theory, where everything is well understood. If I talk about compilers and I talk about the structure of a compiler, I talk about lexing, I talk about parsing, I talk about all these things, everyone that knows the basics of compilers would understand it. What I mean, everyone with computer science background is able to create this very simple compiler, an assembler, and things like that. We have a very good grasp of what it means to create a compiler, but we still haven't got that with model-driven engineering. The other problem is, a bit like AI in the 70s and 80s, there was a big hype around model-driven engineering. And in fact, that hype started before model-driven engineering, to be fair. Before model-driven engineering, before I became a professional programmer, there was a thing called case. And there is, I probably shouldn't really be looking for books while I'm talking, but there is a very good book on case, which unfortunately is not within reach, which I probably recommend. I mean, again, if you're interested in history more than anything else. But case has a lot in common with MD. It also promised that you'd be able to specify a system, and then you'd press a button and the code would come out and everything would just work, and developers would become more or less extinct as the high-level people, the BAs and so on, would be writing code, in other words, creating these specifications. and we would write code that could be proven to be correct and so on. And case failed because, well, for many reasons. First, because what they were trying to do is very ambitious and very difficult, and the tools worked, but they never really worked properly. And at some point, people just kind of gave up on case. The companies went bust and so on. And so, what happened with MDE in a way was that a lot of the clever people that were were involved in case took the good ideas of case and then said, well, why did case fail? Again, I'm kind of rewriting history. This is not exactly what happened, but if you look at the broad trends, you could see as an abstraction that this is how you'd explain this. So the lessons of case were learned, and then we tried to extract the good things and try to get rid of the bad things. So case, for instance, was mainly corporate driven. So there was loads and loads of companies, each with their own products. I mean, the book that I was looking for contains a listing, an entire chapter of hundreds of different case products, all incompatible, all from different companies, medium, small-sized vendors, all sorts. And so once you get yourself into one of the tools, you'd be locked in, and it'd be very difficult to get away from that tool. So vendor lock-in was definitely a big problem with case. Another big problem with case was also that I mean, the 80s were just, technologically speaking, the things we were trying to do. You just require so much more technology, so much more understanding of how things work, and so much processing power. So the good people that learned those lessons decided that the best way to go forwards is to try to create collaborative efforts rather than corporate-driven efforts. To be fair, this was still corporate-driven, but what I mean by collaborative is you have organizations such as OMG, where a whole lot of companies would get together and they would agree on a standard, and that's where things like UML, things like MOF, things like loads of other technologies like ATL and so on, were standardized in open standards that anyone could take and implement. And that was, in a way, a good idea, but the problem then was that companies then took those standards and then created real products. So if you're from the 2000s, you remember Rational Rose, and those products, and even to be fair, some of the talk that OMG had in those days was very much the same kind of talk that Case and AI had before, which was this is going to solve all the problems. Once we got at these levels of abstraction, we will be able to not need to program anymore and so on. And they never really delivered anything close to the end result that they promised. I mean, it's not to say that the tools were entirely useless. Many of the tools were very useful, but if you used Rational Rose, you'd remember that you'd have to have a PhD on menus just to be able to figure out how to use the tool, let alone to actually start modeling a problem domain. Part of it is to do with the theory. So model-driven engineering is very, very complex and very far removed from the usual practice that we got in programming. So perhaps that's what caused the difficulty and the complexity of the software. The other problems is we were not familiar, and we are not familiar, most software engineers are not familiar with the concepts that are core to MDE, and we are not used to dealing with these levels of abstraction. It's not just not how the way we think. And if you think about it, it took us a long time to train ourselves to think like programmers. Most of us that started young, we started thinking like a programmer quite young, and we molded our view of the world from there. And now what's required, a bit like with functional programming, and this is a long-standing argument I have with my friends, what's required is for you to shift the way you think about things. And model-driven engineering is a very different way of thinking about things. And as I said, the tooling is not ideal, really. Given all these problems and these difficulties, I think this is the last slide we got here. So given all these problems and all these difficulties, model-driven engineering never really got the traction that the people that were behind it expected, which basically meant that the ideas are there, they were developed for a very long period of time, and if you want to do anything with code generation, you have to start by reading through all the stuff that they've done, hence why I got involved in it. But it's not very obvious how you'd apply these ideas, because it's the funding and the amount of work that used to happen in MDE was pulled out, just like it happened with AI. Only a few people survived in the field. I mean, they're doing very interesting work, but they're obviously moving in the one direction, and they're building on top of a lot of the work that's already been done, especially over the last 10, 15 years. And if you join in with as a new software engineer, that your purpose is just to try to build a code generator, you have this very, very steep road you need to go through in order to be able to get yourself up to date with the state of the art before you can actually start to think about how you apply all these ideas to your project. And so this is our basic overview of this. So what I'm going to do now is I'm going to switch gears slightly and move over to our notes, which now, in fact, let's just double check that we're doing with time. Actually, we've done half an hour already, so I wonder if it's worthwhile just concluding our overview, or whether we should start getting into more detail. Perhaps we can. Actually, to be honest, we can go into a bit of detail. What we'll do is we will scope our detail to just trying to understand the basic problems there is with the approach, because I think it's quite related to all the discussion that we had so far. I mean, these are not formal lectures, like I said. These are more sort of gathering my thoughts and so on. So we can be flexible here. So, as I said, as a software engineer like myself, I started. How did I get involved in all this? To be honest, this is also a fair, a good way of connecting the dots. So I got involved in model-driven engineering purely because I've since 2010 I've been writing a code generator called Dogen. Now I was part of a team who was working on a code generator, and if you're interested in that, I have written a paper on this subject. In fact, you can probably get it from the main website. So if you want to understand a bit of the context of how I got involved in this, I recommend you read this experience report, which is also available. So I got involved in code generation because all the way back in 2010, because I was part of a team that had to write a code generator, and this paper narrates all of our adventures. And we didn't really know anything about model-driven engineering. We didn't know anything about case. We knew very little about any of this. But we thought about the problem, and if you have to also remember this is the days before protocol buffers. I'm not entirely sure if the protocol buffers already existed, but it was definitely not popular in 2010. So what the architect of our team decided to do is he decided to create something like protocol buffers, but just internally, so it didn't have to have all the support for N languages and so on. We just needed it to support a few languages like Java, C++, and C#, and it was used mainly to create code that was used as a communication between these three different languages. So on the face of it, it seemed like a really simple problem, but because we didn't really have any of the training, and because most people don't have any training around model-driven engineering, we ended up reinventing a lot of the things that people that worked on model-driven engineering already knew about. And we struggled. I mean, as you see in this paper, we did manage to achieve our aims. The system we put in production is still there, it's still working, it's still doing its job. But it was clear to any of us that spent 3 years or so that we spent 2009 maybe to 2012 coding on this, that the first go was not the best go. And so I decided to do to take some of these ideas, none of the code of course, because this is all proprietary code, but some of these ideas and mop them up into what became Dogen. So this is all, Dogen was written from scratch. So around, I don't remember exactly when, but probably 2011, 2012, I started Dogen with the idea of making a 6-month project to rewrite the code generator and to fix all the issues that we bumped into, and address the problems and make it better. And in my mind, that sounded like an absolutely trivial thing to do, because I'd already written, I mean, there were only 2 core developers in that team, plus a team lead, and we wrote all the code from scratch. So I knew exactly how to write the code. I knew exactly how everything hung together, so I thought it was quite straightforward. And my idea was even to create Dogen as a tool for a startup and use it after 3 or 4 months of coding. So it didn't quite turn out that way, as you can see. 10 years later, I'm still working on it. The reason why it didn't turn out that way is because, unlike in a corporation where there's boundaries where you can say, well, you have got 6 months to develop this project or a year or whatever, when you're doing something in your spare time, you can keep following the path wherever it leads you to. And if you keep asking questions, you will keep on getting answers. This is the interesting thing about research. If you start to ask questions of why is this done this way, why is this done this way, you will eventually end up finding somebody who spent a very large chunk of their lives thinking quite deeply about the questions that you are trying to solve. And so, from 2012 to about 2014, I worked on Dogen without knowledge of the industry or the academic environment. And I created a code generator that kind of worked, but it also made me think that it wasn't quite right. There were things that were just strange. I kept on refactoring and refactoring, but I just couldn't. It's as if I was working missing the domain concepts. And it's hard to explain, but it's a bit like, as an example, it's a bit like when you start a job at a new place and it's a different field from where you used to. Like, say for example, when you start in finance and everyone is talking about, I don't know, options and barriers and volatility and volatility surfaces and things like that, and you just don't quite get it. And that's what happened to me when I was coding Dogen. So I just didn't quite get it. And I wrote a number of articles and posts talking about my experiences as I was writing Dogen. You can see them here. And I ended up getting into these never-ending refactoring exercises where I would just start doing things in one way, then I'd get halfway through it, and then I'd figure out there was a better way of doing it, and then I would have to go back and redo everything and so on. And this kind of sort of flip-flopping cycle went on for a while. And then I started my PhD around 2014, and I joined the computational neuroscience lab. And for a couple of years, I was working on Dogen on the side, but I wasn't really doing a lot of progress. And I was mainly focused on computational neuroscience, which in itself is a very interesting field. But I didn't quite really get into computational neuroscience either, because it really requires you to understand a lot of things as a sort of a starting point. You need to really understand lots about biology, a fair bit about maths and so on. So my first couple of years of my PhD were mainly to learn about research. So I spent a lot of time reading papers, reading books, organizing research and so on. And at some point I realized actually that Dogen was a research project. I just never quite saw it that way. But the more I looked into it, the more I noticed it was a research project. It just so happened that there was no one in my university that was working on something like that. So I took a break from the computational neuroscience. It also coincided with my supervisor leaving the university, and I decided to try to see if I could convert the engineering project into a research project. And what that led me to was into the world of model-driven engineering. And one of the things I started with was a book that I still recommend. This book, Stahl and Volta, Model-Driven Software Development. This book was it was the first time where I suddenly realized actually there are people out there that have spent all their lives doing things like this and thinking about this problem quite deeply. And after that, I was very, very curious about all these ideas and notions and so on. I was like, why is it that not everyone is using this yet? And that led me to then start to spend a lot of time understanding what exactly is the field of model-driven engineering and what's the current state of affairs in the field. And that leads us quite nicely to our notes. The product of that analysis is the notes, which is a smallish book, printed is very thin. This is not really a compendium to give you all that you need to know about model-driven engineering. It just gives you, well, to be honest, it's my take on model-driven engineering more than anything else. You can read other books like Brambilla, and you can also read the Voltaire Stahl book that I mentioned there. This is more sort of a quick introduction that's focused on the concepts you need for MASD. So it doesn't really, it's not very suitable as a book for you to learn model-driven engineering. It's more a set of notes for somebody who wants to just get the gist of it so you can get on with MASD. Because if you just try to go straight into model-assisted software development, you're not really going to understand where it comes from and why it is the way it is. So that's how I got into this. So now let's just cover with the remainder of today's lecture. which is another 20 minutes. Let's just cover then that journey into understanding what exactly is model-driven engineering. So the first problem you find when you try to understand what model-driven engineering is, it's very difficult to understand exactly what it is. What I mean by that is most fields, such as and on the face of it as well, most fields seem to have a core set of ideas that are they seem to be composed together into a bundle of things that you can easily say, okay, this belongs to the field or this does not belong to the field. In practice, that's not actually true. As you take something like computational neuroscience, it's very difficult to understand where the field begins, where it ends. But there's always this sort of core set of concepts in the field. And now, model-driven engineering has that core, but it is just a little bit vague. And you see this throughout the literature. And I try to explain this in this is sort of a critique of the field. I try to explain this. It's a bit like programming paradigms. So in computer science, it's very common for us to talk about, I don't know, object orientation as a paradigm. In fact, that word paradigm is a bit meaningless because, as Harper said, the trouble with paradigms is that they're rather difficult to say. It is rather difficult to say what one is, or how we know we have a new one. Without precise definitions, nothing precise can be said, and no conclusions can be drawn, either retrospectively or prospectively, about language design. And that's kind of a fundamental problem we seem to have in a lot of the high-level concepts in computer science. Even object orientation, you may think that it's quite a well-defined, understood concept, but you could have wildly varying interpretations of object orientation, all the way from, say, using C to do object orientation to Smalltalk, which are completely different takes on the same idea. And we think we agree on these terms, but it's not entirely clear that they actually are formal definitions. And of course, the same thing happens with MD, it's being a computer science concept. Some people call it a methodology. We don't even know exactly what we mean by methodology. If you start researching what's meant by methodology, you're going to understand that most computer scientists call methodology something that pretty much everybody else would not call a methodology. And before you know it, you're going to be quite deep into the woods trying to make sense of all these terms, because these terms are not they're not absolute. They're not terms that you could if you can't just take one of these definitions and say, okay, this is the formal definition of this technical term. All these technical terms require interpretation and context. As we've seen before, when we discussed technical spaces and platforms, that's exactly the kind of problem we have with almost every term that is used inside of model-driven engineering. And as I explained, we don't even have a proper definition of what the methodology is in computer science, and it is not clear, or it is very likely, I believe it is wrong to call model-driven engineering a methodology, because normally a methodology is very well defined, and we don't really have that definition in terms of model-driven engineering. I mean, what we'll do is we will cover later on what a methodology is. I don't want to get too involved in that because we don't want to jump ahead too much. But let's just say that from the perspective of what computer scientists call a methodology, you shouldn't really call model-driven engineering a methodology because it lacks a lot of the characteristics of methodology. So what is it then? Well, we could say it's just an approach or a general framework. It's fairly generic terms that you can agree with without it giving you too much information. But it's probably not useful to call it an approach because, I mean, there's so many things that are approaches, right? So the best way to think of model-driven engineering, this was my conclusion, is to think of it as a body of knowledge. Again, if you're a normal human being rather than a computer scientist, body of knowledge probably just means a lot of stuff that goes together. But as a computer scientist, we normally, or probably as a scientist or an engineer or one of those professions, you tend to think of a body of knowledge as the set of concepts that go together with the field. You know, as an example, we have, if you take this definition as an example, so every profession is based on a body of knowledge, although that knowledge is not always defined in a concise manner. So there's this idea that associated with a profession or with a group of tasks or with certain kinds of work, you have this body of knowledge that you need to acquire, that you acquire during your professional life, and then you master that body of knowledge. Um, and where there is no formality, then the body of knowledge is generally recognized by the practitioners. And in some cases, you may actually codify the body of knowledge. So, for example, in computer science and software engineering, some people have tried to come up with a software engineering body of knowledge and so on. So there's this idea of model-driven engineering, that there's a body of knowledge associated with model-driven engineering that you need to master in order to make use of it. And where it begins and where it ends is not exactly clear, because that's a characteristic of body of knowledges, of the body of knowledge, of any body of knowledge. So like I said before, we try in model-driven engineering to create these hierarchies of things. We try to, it's all to do with abstraction. It's very easy to build abstractions on top of each other. So it is a good way to organize the brain, to organize knowledge for the brain in terms of hierarchies. So one hierarchy that is commonly used in model-driven engineering is to say, well, the body of knowledge is subdivided into three kind of concepts. At the top we have model-driven engineering, then following that we have model-driven developments, and at the bottom we've got model-based engineering. So what are we trying to do with this, right? So what we're trying to say is a bit like we used to say with object-based and object programming. So if you remember, a long time ago there used to be this notion of object-based languages. I think Visual Basic was probably one of the best examples of that object-based languages, but probably there are others like Pascal, where the languages had object-oriented concepts, but not all concepts were there. So perhaps you're missing some functionality that, according to the canonical, whatever you mean by that, the canonical object-oriented books, it was missing. I mean, if you really want to get into the woods of that, I strongly recommend a quick look at Meyer's object-oriented software construction. This book really, I think, to me, it defines what is meant by object-oriented programming. And there you would find exactly the difference between object-oriented and object-based. And similarly, in model-driven engineering, there's this notion that, well, maybe you've got models somewhere, you're using models in some kind of way, but maybe these models are just incidental to your development process. You're kind of doing bits and pieces in a, I don't know, maybe a diagram or something, and using that to communicate with your team, but the models are just another artifact that gets thrown away in the process of learning about some domain or other. You enter the model-driven development when actually no, the models now are just as good as source code. They're quite central to your development. You are really focused on using models as the thing that drives the development process. And finally, when you enter this sort of level of in model-driven engineering, when you are not just doing the development process, but all the tasks related to software engineering are to do with models. So in this particular case, we're talking about things like testing, deployment, requirements gathering, all of the activities that are required in order to engineer a system. All of them are done using models. I think it's not, again, as with many things in model-driven engineering, it is not necessarily obvious how this works in practice, as it is with object-based programming. I think that this abstraction is good if you're trying to explain something to somebody, but in practice I don't think you're ever going to find where you are in this. None of these things are precise, and so because they're not precise, they're less useful. So I think it's more important to get the general idea that you need to use well, you should be using models to drive a development if you use model-driven approaches, than it is to understand those fine-grained definitions between the different kinds. Apologies, need to cough. Pause for a second. I think I got a cold coming. So we are getting quite close to our time. And to make matters worse, it's not just this problem between MD, MB, and so on. And the truth is, it's a zoo, really, a jungle, as Mambili called it, of different approaches that are related to MDE. So all of these things you see here are approaches that were created over time, and they're all now part of this umbrella of model-driven engineering. So I'll just cite a few. Model-driven software engineering, which I just showed you. Model-driven software development. In fact, model-driven software development is STAL. Model-driven architecture, which is the OMG interpretation. model integrated computing, model-oriented programming, which I find quite interesting as well, model-based systems engineering, and there's many others of these. So each of these will have their own definition of what they think the field is and how it's supposed to work. And because they are really similar, once you abstract yourself from the details, they end up being called MD variants. So there's this notion of the body of knowledge, and then there's this notion of the application of the body of knowledge in a specific variant, or variant or flavor. And to talk about the variants in general, we use this definition of MD star. So if you just basically mean any of the model-driven approaches, you normally just say MD star. But the idea is that model-driven engineering is a superset. It's the body of knowledge that encompasses all of these approaches and all of the model-driven related techniques and so on, or tools, I guess you could say, all fit within this superset. And of course, if you then have to ask the obvious question, which is a question I ask myself, is, I mean, where does it end? I mean, at which point do you know that you've learned at least an overview of all the tools in the toolbox? It is also not very clear, because many things are not obviously outside or inside of model-driven engineering. So as an example, a core concept that I find with model-driven engineering is the notion of product families. But it turns out there's a whole discipline called software product line engineering, which has spent a lot of time talking about product lines. And a lot of the concepts that they've created are very interesting in terms of model-driven engineering. But because they didn't use the same terminology, there's a mapping exercise required in order to get the two to work together. And like that, there's many others, such as generative programming, domain engineering, and so on. So it's not very obvious at which point you could say, well, I've understood the basics of model-driven engineering. You end up having to do some empirical searching across the domain. And for me, as soon as I learned enough of the technologies to explain the work I was doing at Dogen, I considered myself to have completed my learning of the domain knowledge, of the book of knowledge. Does not necessarily to mean that I now know the book of knowledge, it's just that I know enough to get going. And that's the best I could do. And which takes me to the next step, which is the importance of pragmatism. So we have this problem of fuzziness. Part of it is just a computer science thing, as I said, to do with pragmatism, not to do with pragmatism, to do with paradigms and so many other terms in methodology and so many other terms in computer science that we all think we know what we mean by those words, but in reality we don't really have formal definitions for any of those terms. So that the part of it is exactly the same kind of problem. Part of it is also to do with the fact that model-driven engineering is newer than a lot of the concepts in computer science, such as compilers and so on. And the other part of it is that sometimes one just has to get on with work. So for example, when it came to MASD, at some point I just decided that I'd learned enough and I progressed. Instead of spending time trying to create foundational definitions in model-driven engineering, I just assumed that those tasks were too hard and unrelated to the task at hand, so I moved on to my task at hand. So presumably this happens to a lot of people that get involved in the field, and so the field doesn't really get this work on the fundamentals, like maybe maths, for example, where we have somebody like Russell that spent ages working on Principia and so on. So what we end up with in sort of the approach we all end up with is this pragmatic approach. So we know we have a fuzzy discipline, so we must be pragmatic. So instead of looking for formal definitions, we need just engineering definitions, just something that enables us to cut code. I quite like this expression. We just want to get on with the coding. So we look for the minimal amount of knowledge of the domain of model-driven engineering that's sufficient for us to progress into the actual work. And in a way, maybe this fuzziness is not a bug. Maybe it's a feature. What I mean by that is, if we stop to think about the fundamentals of a discipline before we actually start to use that discipline in anger, maybe we're never going to find the fundamentals. Because I think that a lot of the work that gives you understanding of the fundamentals is empirical work. You need to spend a lot of time really digging through the fundamentals and putting them in practice, more like it, in order to be able to make a statement about what's what. and that work is empirical. You can't sit down and think quite deeply about programming in order to learn the fundamentals of programming. You need to actually do programming. And similarly with model-driven engineering, you can't just sit down and learn the fundamentals. You have to actually to really spend time with the concepts in order to be able to really learn them. And so, as a result, my research, I ended up with this sort of definition, not definition of model-driven engineering. Instead of a definition, I went for a characterization because it's not really a definition. So, in my mind, model-driven engineering is an informal body of knowledge centered around the employment of modeling as the principal driver of software engineering activities. So there's this notion of an informal body of knowledge. We don't know where it begins, we don't know where it ends, but we can loosely understand that there's stuff around modeling we need to know in order to be able to start using MDE. And then, because of all this informality, we need the pragmatic application of this family of related approaches to the development of software systems. That's important. So it has to be pragmatic, and we need to get on with the actual empirical work before we can go back to the theory. I mean, we could continue the theory as you go along, but I think part of the work has to be the empirical work. And the other thing that's very important is your objective is to generate automatically either a part or the totality of a software product. And you must do so from a set of formal models and their associated transforms. So these are core characteristics of the field. At the center of the field, models and transforms have to be there. And the automatic generation from those models over to whatever the implementation level details are. Then I also concluded that MDE is not really concrete destination. I don't think you could ever say I am actually developing in an MDE way. I think you can say you are using characteristics of the model-driven engineering approach. And there's always more you could be doing. And it's a vision that should guide your direction, but you're not going to arrive there. You're going to keep going, and it's going to always be there somewhere in the horizon. And finally, this was my biggest conclusion, I guess. It is the responsibility of each MD practitioner to select the appropriate tools and techniques from the body of knowledge in order to apply MDE in an adequate form to a specific instance of the software development process. This condenses a lot of knowledge here. It's hard to explain this in words, but what I'm trying to say is that each individual project that uses MDE is going to be fairly unique. The reason why is because we have this vast toolbox of the approaches and vast set of tools. They are all completely different, and they all work in a slightly different manner. You do have the same conceptual model, but the instance that you're going to create of the application will make it so specific that you're going to, in a way, you're going to become an expert of an MDE variant. You can't avoid that. You can't avoid creating MDE variants because MDE itself is too high level for you to actually deal with in concrete terms. You need something that approaches a methodology in order to actually do work with MDE. And now you may not realize you're creating a variant. That's why I say implicitly. In my case, I ended up doing an explicit variant. But you're always going to end up with something that's going to be very specific to your approach. So that if we go back to our example of the paper that I wrote, the experience report, this is an example of an MDE variant that we created that is only used in that particular company. And in order for you to understand this variant, you need to really spend a lot of... I mean, of course, if you understand MDE, you would have the high-level constructs needed to understand what we did. But you still need to spend a lot of time with the specific instance that we created and understand the tools, the techniques, the processes, all the philosophy, all the things that effectively are a methodology. So we without noticing, we created a concrete methodology for the development of this particular application. It's just that we didn't know we were doing that. But that is almost always what will happen if you apply MDE. It's a bit like saying, if you apply C++, I mean, there is no such thing as applying C++. You need a concrete application of C++. So in one team, you can have an instance of C++ where everything is completely object-oriented. You're not allowed to call a function. You have very strict rules on your code guidelines and so on. And you can have another team where their application C++ is completely procedural. You're not allowed to use templates. You're not allowed to use objects, and we're still using C++. So it is you will have to go to that team and you have to look through that code in order to be able to get yourself into the mindsets of the people working in that product. And similarly, once you apply MDE, you will also have to do the exact same exercise. So it seems that what we're trying to say here is that it's best to create an explicit variant, because then at least you know what you're doing. You're making decisions consciously rather than unconsciously. And that kind of guides a lot of the argument that we're going to make much later on after we've gone through all of this for MASD. This need for an explicit understanding of what it is that you're doing. And I think that should be about it for today, I think, because on the next video we shall talk about models and transformations in greater detail. That should be quite interesting. So okay, that's all for this lecture. Thanks very much for watching.